All right, so welcome to Math 383 Complex Analysis. This is, I believe, lecture 30. So you're at the tail end of the semester right now. What I really want to do is I want to use the last few classes to talk about some interesting applications of complex analysis. So we started talking last time about using complex analysis to estimate integrals. And to some extent, this is interesting because we've spent so much of the semester learning how not to actually integrate. And to some extent, we're still doing that. We're saying, well, yes, this is the integral I'm supposed to do. Rather than doing this integral, I'm instead going to approximately tell you what the answer should be. Very, very powerful technique. And what's lurking in the background is that discrete problems are difficult. Continuous problems are often much easier. You have the powerful tools of calculus to throw at it. So we want to convert discrete problems to continuous problems. So we're going to finish up the Stirling formula, and then we'll move to another discrete problem. And then as time permits, I'll talk a little bit about eigenvalues of Hermitian matrices to prepare for some applications lectures on random matrix theory and L functions that will be coming later this week and early next week. All right, so the first few slides are going to be very familiar. This is just to remind us of where we were. It would have been nice in like 10 more minutes yesterday, but I really wanted to talk about the integrand approximation and try and get a sense of what's the right scale. So we have the gamma function, which is s minus 1 factorial. And we talked about how we write it as s minus 1 because this gives us the invariant measure dx over x. If I rescale x by a factor of 5 or 6 or whatever, it doesn't change the ratio dx over x. Stirling's formula says n factorial is about n to the n e to the minus n squared of 2 pi n. We're going to see where that comes from. The big thing we were using is this idea that we have some functions, capital Phi, capital C, capital Phi, lowercase c, and we're assuming that capital Phi has a bunch of conditions. We're assuming it has a minimum at x naught. We're assuming the second derivative is greater than 0. So is that concave up or convex up? Concave? Concave up. So we know it looks something like this, roughly. And so curve sketching is a technique that has really left the calculus curriculum. How many of you had to learn how to sketch curves by plotting first derivatives, second derivatives, putting all the, oh, wonderful. Okay, when you're teaching and you ask this question, it'll be interesting to see if any hands still go up. There's a few things where, as the computer comes in, certain skills get relegated to, you can look it up if needed because the computer is just so present now. But it's nice to be able to just put down some rough pictures and get some intuition from this. If we are looking at e to the negative s phi of x, if you are just a little bit away from the minimum value, because s is going off to infinity, that's going to mean an incredible change. It's going to be significantly smaller. And again, we were talking about what scale to move. The scale that I move is a scale relative to s. If I move over 1 over a quadrillion, it sounds like I haven't moved that much, but as s goes to infinity, moving over 1 over quadrillion is a tremendous amount. Think of this as like a Gaussian. The variance is on the order of 1 over s or 1 over square root of s, something like that. So any fixed absolute number is going to be so many standard deviations away, it's going to be essentially nothing. What you really want to do is you want to talk about movement on a scale of size 1 over s or of size 1 over square root of s. And so if I move over on the order of 1 over s in terms of the value of x, how much is that? Well, we talked about the Taylor series expansion. We can write, phi of x as phi of x naught plus phi prime of x naught plus phi double prime x naught x minus x naught squared over 2 factorial plus something of size x minus x naught cubed. Well, the phi of x naught is fixed, so it doesn't really affect anything. It's just changing, for those of you who know physics, where I'm setting my potential to be 0. We're assuming phi prime of x naught is 0, so that's not present. So really, when I look at phi of x, it really looks like phi double prime at x naught times x minus x naught squared plus a term of size x minus x naught cubed. So what this is telling me is if I move 1 over square root of s away from x naught, then when I square that, that's of size 1 over s. When I hit that with s, There's essentially no change. It's just like a constant shift. So it would be like decreasing my magnitude by a fixed constant factor. If, however, I move over, say, 1 over s to the 1/4, well, then I would have 1 over square root of s. When I multiply it by s, that would be a square root of s in the numerator. And now I would have an incredible decrease in the contribution. So this is telling me that I expect there to be a contribution when I move on the order of 1 over square root of s from x0. Maybe a little bit more, throw in a few logs to be safe, up to, say, log of s over square root of s, or log of s to the nth power for some fixed n. Something like that, I expect there to still be contributions. Beyond that, there should really be no contribution. Yes? Because we know this is the global minimum. So the minimum of big phi. So we assume psi has some nice properties in terms of its decay. Right? And so, but again, remember, psi is fixed. So psi is fixed. It's a fixed function. As we move over here, we have e to the negative s. S is going to infinity. So we're going to assume all the integrals exist. So because all the integrals exist, it's a fixed contribution essentially coming from the side. But as you move and take s going larger and larger and larger, it's going to be weighted by something smaller and smaller and smaller. So as x moves away from x0, the contribution is going to become negligible because we're multiplying it by e to the negative s phi of x. Your contribution of psi of x is fixed, but what you're weighting it by is getting smaller and smaller and smaller. So even if psi of x was large for a little bit, we are assuming that everything converges. So we have to have some decay conditions on psi. But whatever they are so that this makes sense, as we move away, it can't contribute. So it's telling us that the correct scale is roughly of size 1 over square root of s. Okay, and so the result, and we talked about why this was a reasonable result, is the e to the negative s phi of x0. Well, that's just pulling out the constant term. And then we saw the square root of 2 pi, the phi double pi, and this is coming from it looking like a Gaussian. And so near x0, c of x is approximately c of x0. And so that's where the c of x0 is coming from the numerator. Your phi of x is basically your phi double prime x0, x minus x0 squared over 2 factorial. And so this is where that is looking like e to the negative s phi double prime of x0, x minus x0 squared over 2. It's looking like a Gaussian. It's looking like a Gaussian with variance 1 over s phi double prime of x0. And so if I have a Gaussian with variance 1 over s, phi double prime of x0, phi double prime of x0 is fixed. 1 over s for my variance, my God, that's going to 0. So as this gets large, the Gaussian is becoming tighter and tighter and tighter. What does this remind you of? Something we've seen earlier in the semester? Approximations to the identity, where essentially all the action is happening at one point. This is essentially what's going on. All the action is happening near x0. It's very similar if we let s be an imaginary number where there's going to be huge phase oscillations. It's only going to be at the minimum point where you're going to have anything that really contributes. So what we want to do is we want to basically say it looks like a Gaussian, very, very close to x0. On what scale? Well, we're talking about a scale roughly of size 1 over square root of s. If I'm moving 1 over square root of s, then my c of x is not really changing. Because, again, s is going to infinity, so moving 1 over square root of s is essentially not moving at all. And so we're basically saying the contribution from any other part of the integral is so negligibly small that we can basically just reduce the integral to what's going on over there and then just keep the errors. So that was the main idea. And then putting in the details, we first have an integral from a to b, and then we want to do is we want to replace it with an integral tight about the point x0 and throw everything else away. And then now that we're tight near x0, we look at what we have, and we see that it's really close to a Gaussian. I replace it with a Gaussian and keep track of what the error is, and then extend the integral to all of infinity. So that is the main idea of the proof, is we do a sequence of approximations and we keep constantly vigilant as to what are the errors when we're doing this, so that at the end of the day, we actually have a theorem. The more carefully we do this, the more we can say about what are the error terms. So what the book is saying is that if you do this carefully, you get an error term of size 1 over s. Well, actually, not quite. What is the size of the error? Nope. What's the size of the error relative to the main term? How much smaller is the error than the main term? 1 over square root of s, because the main term has an s to the 1/2 in the denominator. So the next term is a 1 over s. So it's 1 over square root of s smaller. So it's a lower order term. We get the main term behavior, but we don't have necessarily the greatest error estimate. That's okay. It's still good enough. Okay, so now we want to do the calculation in detail. So without loss of generality, let's assume phi of x naught equals 0. Okay. And so we can write phi of x as phi double prime of x naught, x minus x naught squared over 2 factorial plus, I'll call it, some term g of x. Okay. So we want to integrate from a to b of e to the negative s phi of x c of x dx. So this is going to be the integral x minus x naught is less than, let's say, some delta of s, plus an integral x minus x naught greater than delta of s, a less than equal to x less than equal to b. So step 1 is we want to show that this goes to 0 as s goes to infinity. And the whole point is we want to figure out what is the correct scale to look at for delta of s. So if you know what the answer is, you can use the method of divine inspiration, right? How does the method of divine inspiration work? You write down what the answer is and then you show that it works. What is the problem with the method of divine inspiration? You need to know the answer beforehand, or you need to be divinely inspired, or somebody who knows the answer needs to be able to send it to you, right? When you're taking an exam, it is not always the best to count on being divinely inspired, right? This is why when I was an undergraduate, I always told my friends, I don't know how long it's going to take to do the problem set. It's a math problem set. It's a physics problem set. Until we find the right way of looking at the problem, you're a philosophy major. You know, or you should know how many pages you read an hour. You should be able to do the subtraction problem where you have to end and where you stop. And you should be able to roughly estimate how long it's going to take you to read, however many pages you have. And you should know roughly when you're in math, it's until you find the right way of looking at the problem, you don't know how long it's going to be. This is why I love using parameters. We did this when we looked at the integrand. We said, well, look, we first looked at where the integrand was largest. We looked at the critical point and we saw that x equals n. Then we looked at n plus 1 and n minus 1 and we saw, wow, there's really no change in the integrand. Then let's move a little bit more. Let's look at n plus n to the c, where c is a free parameter. And how far can we push it? And we saw that we could take c less than 1/2 without any trouble. When c was around 1/2, then things were getting interesting. But it gave us a sense, so we could try something similar here. Let's let delta of s. Now, how do you want to write the free parameter as a function of s? There's 2 natural ways. You could write it as s to the c, or there's another way of writing it. You could write it as 1 over s to the c, right? In the first case, if I'm writing it as s to the c, what can you tell me about c? What's your intuition telling you if I write it as S to the C? What should be true about C? So if C is positive, that means S is going to infinity, and we are making a tremendously large motion. If that's the case, then we're not going to be localizing at all near x naught. We're going to essentially cover the entire real line. So what is your intuition about C if we write it as S to the C? Well, if it's fractional, like 1/1000, it's still going to be going to infinity. It would have to be negative. So if you write it as S to the C, here, C is negative. If you write it, I'm sorry? I'm sorry? We're looking at a slightly different problem here. We're no longer looking at the integrand, for the Stirling formula. We're looking at the integral e to the negative s phi of x. We're looking at moving just a little bit away from the point x naught. If you have s to a positive power, since s is going to infinity, that's a huge movement. So if I'm writing it like s to the c, I have to keep in mind that c is going to be a negative number. This is a matter of personal preference. You are allowed to discriminate. Do you want to work with negative numbers, or would you rather work with positive exponents? I'm sorry? I would rather work with positive exponents as well. Why? Well, I have some information about the quantity. Let me explicitly incorporate that information in how I'm writing this. So if I write it as 1/s to the c, I'm explicitly incorporating the fact that I know I've got to be moving a small amount. So I prefer this. So now c is positive. And what else do we know about it? Any thoughts about how large it could be?
Less than 3/4.
Okay, why 3/4?
Because it's definitely less than 1. And it might be, and we know that at step sizes of 1/2, we might be on the order of the shift that if we look at it like a normal distribution, that might be approximately 50%. So just taking something into
Okay, so 3/4 is not necessarily a bad choice. If we took c equals 1, do we think that's too small? We already know just from our quick heuristics that we should be able to move 1/square root of s and not have much of a change. If I look at e to the s phi of x naught versus e to the s phi of x naught plus, say, 1/square root of s, this is approximately e to the s phi of x naught plus s phi double prime of x naught. 1/square root of s squared is just going to be 1/s, and then we have a factor of 1/2. The s and the 1/s cancel, and this is looking like e to the s phi of x naught times e to the phi double prime of x naught over 2. So as s goes to infinity, the e to the phi double prime of x naught over 2, that's going to stay roughly the same size. It's going to be a constant rescale that's independent of s. So I really should be able to move over at least 1/square root of s without having any significant change. So if I just took c to be 1 and said I only want to move up to 1/s, that's not a large enough window to capture all the action. So my window should be at least as large as c equals 1/2. Right? So in terms of just trying to find out what the window is. So then the question is, should it be, the exponent should be larger than 1/2 or less than 1/2? I think it should be a little bit less than 1/2. The way we're writing it. You could, of course, as write it as s to the 1/2. I'm sorry, 1 over s to the 1/2. Taking into account we know something like that, and then maybe minus a little bit, because we want to be able to move just a little bit beyond that. So there's lots of different ways that you can write things, taking into account what you know. Again, this is why I want to spend the time talking about this rather than just blasting through at warp speed, how you do the calculation. How do you actually come up with these arguments? How do you actually come up with how you approach something like this? You need to find the correct scale to study the problem. And the correct scale is looking like roughly square root of s, 1 over square root of s. Do I want to be a little bit more or a little bit less? If I'm a little bit more, then that means I haven't moved far enough and I'm not seeing all the action. So I think I would want to write it as 1 over s to the 1/2 minus c. I think that's the right way to look at this. And so if the standard deviation is of size 1 over s to the 1/2, this is the same as s to the c over s to the 1/2. So it's s to the c copies of the standard deviation. How many standard deviations have we moved? S to the c. As s goes to infinity, that means we've moved essentially infinitely many standard deviations away. Who here has taken a good probability of stats class? Okay, you've seen the central limit there. If I take a normal distribution and I move just 10 standard deviations, what's the probability that I'm more than 10 standard deviations away? For all practical purposes, yeah. But basically, 10 standard deviations away, the probability of being that far or further is essentially 0. You can calculate precisely what it is. There's nice ways to estimate that. It's essentially 0. And that's a fixed number of standard deviations. This is now moving s to the c standard deviations away. How many of you are familiar with Chebyshev's theorem from probability? The probability that you're at least k standard deviations away is at most 1 over k squared. Chebyshev is enough to come to the rescue here. And using Chebyshev gives you a 1 over s to the 2c, which is enough to show that the probability is going to 0. Or equivalently, that the value of the integral is essentially going to 0. So I would expect that we want to move on the order of 1 over s to the 1/2 minus c for my delta of s. That's roughly the scale I want to look at. Okay. And so now, as we continue, so we'll have, take delta of s to be s to the c over s to the 1/2, with 0 less than c clearly less than 1/2. And this gives me the natural scale to work on this. So we'll have the integral from a to x naught minus delta of s plus the integral from x naught plus delta of s to b e to the negative s b of x c of x dx. Okay. And we now need to just make some kind of estimates as to what's going on. So, the question is, what do you want to assume about c of x? The more decay you assume about c of x, the better. But we are going to have some nice decay, here already with the e to the negative s v of x. Okay. So let's try to think, how much is it going to be if we're at least delta s away? Well, because my function is concave, what do I know as I move further away from x naught? Yeah, it's increasing. And if it's increasing, then I'm multiplying it by an even smaller exponential, right? So if I look at the e to the negative s v of x, the largest that's going to be is when I'm at the point x naught plus delta s or the point x naught minus delta s. So e to the negative s p of x is largest at the x naught minus delta s or x naught plus delta of s. So we would have, e to the negative s phi of x naught plus phi double prime of x naught. And then we have x minus x naught. So that's going to be delta of s squared over 2 plus something of size x minus x naught cubed. So that'll be something of size delta of s cubed. Okay. So when we look at this, we're still going to get the e to the negative s phi of x naught, exactly as before. The next piece is going to be an e to the negative 1/2 phi double prime of x naught. We have a delta s squared times s. Oh, well, delta s squared is going to be s to the 2c over s. The s is canceled. We'll get an s to the 2c. Right? And then the next piece is going to be big O. And now we have a delta s cubed. So we'll have an s to the 3/2 down below times an s upstairs is going to give you a square root of s down below. So we'll have an s to the 3c divided by s to the 1/2. Okay. This gives me a little bit of an idea of what I want to be true for, maybe 3c. So if I look at the second term, as s goes to infinity, what happens to this term? Goes to 0. Goes to 0 very rapidly. Goes to 0 rapidly as s goes to infinity. What about the next term? So if c is small, it goes to 0, goes to 1. So if c is small, then you're going to have basically an exponent that's going to 0, so it's going to go to 1. But does that really bother us? No, because we've already got the middle term going to 0. And if c is large, does that bother us? Why? If you could be going off to positive infinity, right? We do not want to have an e to a growing infinity. So what do we need about 3c? Less than 1/2, or c less than 1/6. So basically, we had the 1/2, and then we have an extra 1/6 that we have to be a little bit careful about. So as long as we take c less than 1/6, then we should be okay in this argument. And then all of those other terms are really not going to matter. And the meat of the argument is going to be coming from the integral from x naught minus delta of s to x naught plus delta of s. Essentially, we're just saying we've moved far enough away that the contribution is negligible, which makes sense because as s is going to infinity, you have an e to the negative s phi of x. The smallest point of phi of x was at x naught, and we're moving away from it. So any small movement gets magnified tremendously. And then you just need to assume a little bit about c of x so that these integrals actually converge. All right, so sometimes rather than putting down all the different conditions, you just extrapolate, I need the following, and then when it comes time to actually use it, you just check and make sure that it actually works in practice. Okay, so now we're reduced to integrating from x naught minus delta of s to x naught plus delta of s, e to the negative s phi of x, c of x dx, where delta of s was x to the c over x, I'm sorry, s to the c over s to the 1/2, 0 less than c less than 1/6. Okay, because we are moving such a small range, you can approximate C of x with C of x naught. So as delta S so small as S goes to infinity, C of x is approximately C of x naught. And then similarly, you show e to the negative S phi of x is approximately e to the negative S phi of x naught, e to the negative 1/2 S phi double prime of x naught, x minus x naught squared, and then times e to the big O of x minus x naught cubed. So that's just using the Taylor series expansion. Because delta S is fixed, this is a fixed number. This is looking like a Gaussian. And this, what does that go to? Because we're moving a very small distance from x naught, what does the last factor go to? 1. So the integral is approximately the integral from x naught minus delta of S to x naught plus delta of S, e to the negative S phi of x, phi of x naught. And then we have e to the negative x minus x naught squared over 2, 1 over S phi double prime of x naught dx. And this is essentially the integral of a normal. I'm missing the correct normalization constant. But I'm integrating a normal, and the number of standard deviations I'm doing is growing with S. Just doing a fixed number like 10 is already enough to get essentially all the probability. If I do log of n standard deviations as n goes to infinity, I basically get everything. So now, as S goes to infinity, we get all the probability. And this is the high-level sketch of what's going on. And again, the real thing to remark here is the power of finding what is the correct scale to study. How many of you have done measure theory? Where you've done basically, you first take your simple functions that are just indicators of intervals, then you look at combinations of intervals, and then you get from this to the step functions, and I think it's the continuous functions, and you keep moving up like that. It's a very similar process here. We break down the integral into here's the action, focus on what's going on there, and because we're now just looking very close to x naught, we can throw away the rest. And because we've thrown away the rest, we can then approximate it with a Gaussian. And then we extend back. We would not want to do the approximation in the very beginning, because as we move far away, there could be some issues. So we first localize, show that what we've thrown away doesn't matter, deal with how we approximate there and say, all that really matters is the main term. And then if you really want to prove the theorem, then you just have to roll up your sleeves and do a better job of keeping track of the errors. All right, so in terms of now applications, we want to apply this to Stirling's formula. So we want to prove what is n factorial. Well, we want to use the theorem. And so I repeated the theorem in extremely small font over here. Right? And so we need to define what is big phi, what is little c. Well, we have e to the negative x, x to the s, dx over x. And I can write this as e to the negative x, s log x, dx over x. Okay? Is this looking like what we had before, e to the negative s phi of x? Does this look like e to the negative s phi of x? Yes or no? No. My argument of the exponential is not s times phi of x. I have x, negative x plus s log x. The log x is looking good. The negative x is not looking so good. Any thoughts on what I could do?
Rescale?
Rescale, how do I rescale?
Take x to be s times x.
Yeah, let x equal s times x. And now we have gamma of s is the integral from 0 to infinity, because Doesn't change when I rescale. Now we'll have e to the negative sx plus s log x. And what's true about dx over x? It stays the same. I've rescaled x to being s times x. So dx over x is still dx over x. So I'll write it as 1 over x dx. We find, I'm sorry?
Log SX there?
Oh, yeah, yes, thank you. So log sx, yes. When I rescale x, I have that over there. But the dx over x, so we're using dx over x goes to dx over x. We're finally using that we have this invariant scale. Well, now if I want to write this, this is now just the integral from 0 to infinity, e to the negative s. I've got to be a little bit careful. I'll write this as x plus the log of x. And now I also have this s log s term. So I'll just pull that out, e to the s log s, 1 over x dx. So I'll pull that out. So I have an e to the s log s. What is e to the s log s? E to the s log s is just s to the s. It's e to the log of s to the s, yes? Yes, I do, thank you. And so we get an s to the s, integral from 0 to infinity, e to the negative s, x minus log of x, 1 over x dx. What is big phi of x? It's just x minus log x. What's phi prime of x? It's just 1 minus 1 over x. Phi prime at what point is going to be 0? 1. And thank you for using that figure. What's phi double prime of x? 1 over x squared, which is always greater than 0 in our region. Yay, conditions are met. Right? The function c of x is just the function 1 over x. Now that function is not integrable. So you have to be a little bit careful, but it at least has some decay. And so we're going to be okay. And so now things are basically set up so that we can use the formulation of the theorem. Okay. Any questions about this? So it's not immediately clear that this is a situation where the theorem applies because we didn't have it of the form e to the negative s phi of x. The cleverness was doing a change of variables. And there's a lot of problems like this where you can do change of variables. When I teach probability, I mention all the time how you can find a lot of these integrals by changing forms and just recognizing the correct functional form. How many of you know about beta distributions? So when you're trying to find like the beta distributions or chi-squared, you can do changes of variables like this, and you can pull out the key parameters, and then you're left with something. And what is true about the integral of a probability distribution? It's 1. So if you can recognize, hey, when I look at the variable part of my distribution, it looks like a Poisson, it looks like a beta, it looks like a chi-squared, and then I've got this integral floating around that's just a fixed value. That's just absorbed into the integration constant. It's absorbed into the normalization constant. I don't have to compute it. So this is an extremely powerful idea. So we can now use our stuff. What I'm going to do is I'm going to just share just very, very briefly a couple of slides on logarithms and the method of least squares and regression. How many of you have never taken a stats class here at Williams? If I talk to you again in a few months, I don't want to see your hand up. Especially if you're a senior, take a stats class before you leave. This is the 21st century. One of the most useful skills you can get is learning how to analyze data. And so if I have a relationship y equals b, but how many of you have taken a stats class? Let's do it on the affirmative. Okay, so you've done regression, linear regression. So finding it. So we have a procedure that uses multivariable calculus to find the best fit line to data. And it's beautiful for linear relationships, but most things in life aren't linear. But a lot of things in life are linear after you do a logarithmic change of variables. So if I have a power law relationship, y equals bx to the a, if I take logarithms, then I get the log of y is linearly related. It's a log of x plus b. And so one of my favorite examples is Kepler's third law. If t is the orbital period of a planet, then the orbital period squared is proportional to the cube of the length of the semi-major axis. Well, instead of doing squares and cubes, you can always just take the square root and say the period is proportional to the length to the 1.5 power. Kepler came up with this by pouring over data from the planets. And it was masterful work to get, planets travel in elliptical orbits, they sweep out equal areas equal time. This was the key for Newton eventually deriving the law of universal gravity, trying to explain these orbits. Let's look at some data. And the data list is a little bit smaller than it would have been when I was presenting as a kid. We're down to 8 planets. And so I'm giving you the length of the semi-major axis in astronomical units. And I'm giving you the orbital periods in years. If you look at this, can anybody tell me what the constant b should be? Is there any planet that might help you figure out quickly what b is? Earth, right? We've chosen units so that Earth basically, its length is essentially 1 in this unit of measurement, and its orbit period is essentially 1. So in this series, b should essentially be 1. I've chosen it to be, well, it wasn't that on the previous slide, right? This is using, beautiful tech. So, seriously though, when you're giving presentations, especially in the Zoom era, when you're talking about parts of equations, use color. And do not feel like the NFL that had the Jets-Bills game where they used red and green, and it just looked like, for the people who are colorblind, 22 people plus the referees all in black, just diving at the ball. I will try to remember to send the clip, just how somebody showed what it would look like if you were colorblind. And it's a great warning about when you're trying to be clever or whatnot, you can fail miserably. If you plot the log, the log of the period versus the log of the semi-major axis, absolutely brilliant, how well it fits. And when you do the analysis, you get so close to 1.5 in terms of just numerically discovering Kepler's law. So here's one of my favorite plots. This is the plot of the rank of various words in the English language versus their occurrences. When you do a log plot, you see a beautiful straight line. And this is a real world straight line. It's not a perfect fit because in the real world, it's not going to be perfectly aligned like physical law. You have fluctuations, but you have a very good, strong linear relationship spanning several orders of magnitude. So we have 7 minutes left. That's just enough time to do hopefully one of my favorite problems. So I give you a number S, and I want to write it as a sum. Each AK is greater than or equal to 1, and I want to maximize the product A1 through AN. So N is free. Can somebody tell me quickly some thoughts about the A's? You don't have much time. Got to be fast. Got to think quickly. Positive. Well, I told you there are at least one, so thank you. Do you think any of the A's are 1? No, because it's not going to help the product. Do you think any A is as large as 10? Do you think you have a summand as large as 10? What could you do if you had a summand of 10? Okay, if you have a summand of 9, replace it with 7 and 2, 6, 4 and 2, 5, 3 and 2, 4. I can replace that with 2 and 2. I'm indifferent. Let's get rid of 4. So we know each summand is either a 2 or a 3. Which would you rather have, 2s or 3s? Why 2s? 2 plus 2 plus 2 versus 3 plus 3. This gives you 8. This gives you 9. So it turns out you want to have as many 3s as you can, and if you have anything left over, you do it as 2s. And if you have just the number 1 left over, if you're doing 100, then you put that 1 in with 1 with 3, and you make it 2 2s. All right, so in the discrete problem, we saw that it's best to have a bunch of 3s. Does anybody know why 3 beats 2? Yes. What is really looking in the background is this is all about the number e, and e is closer to 3 than it is to 2. So let's look at the continuous version. So s is a1 plus an, and they're real numbers. And we want to maximize. So we still know, 1 less than equal to ak less than equal to 4. And I'm going to do less than or equal to, so I have a compact interval, and so I can use some results from real analysis. What I'm going to do is for each fixed n, I'm going to find the maximum product. When n equals 1, not too hard to figure out what to do if I only have one summoned. What if n equals 2? What's the best? Square. So when n equals 2, each ak is s over 2. What do you think is true in general? What do you think is true? Yeah, s over n. So I'll leave that as an exercise for you to prove that in the general case, there has to be an optimal choice because it's compact. If you had 2 things that weren't equal, then you can just go back to the case n equals 2, and you make them larger by replacing them with their average. So everything must be the same. Or you can do Lagrange multipliers, so they all have to be the same. So let's look at the function f of n, which is going to be s over n to the n, and we want to maximize over 1 less than equal to n less than equal to s. So it should be pretty clear that the maximum is not going to occur when s is equal to 1, when n is equal to 1 or s at the extreme cases. This is an integer valued function. It's hard to find optimal points of integer valued functions. However, let's look at this function, s over x to the x, or e to the s over, e to the x log s over x. Okay. If I look at this integer valued function, that's hard to deal with. If I look at this continuous version, much easier. What is f prime of x? All right. This is going to be just f of x, and I have to take the derivative of x log s over x. If I want, I can write it e to the x log of s minus the log of x. So if I'm doing this correctly, the derivative of x is 1, so I get the log of s over x plus x. And now I have to take the derivative of the log of s over x. So the log of s is 0. The log of 1 over x is going to be negative 1 over x. So this should just be negative 1 over x. So it should just be f of x times the log of s over x minus 1. So it's just f of x, the log of s over x. And what happens with the minus 1? Minus 1 is the same as the log of e, is negative log e. So that's just s over ex, e times x. So when is this 0? Equals 0 if s over ex equals 1. Therefore, x equals s over e. So when you look at what's going on, here's f of x was s over x to the x. F prime of x was f of x times the log of s over ex. So here's x, here's f prime of x, here's 0, here's s. And we saw that the critical point was when x equaled s over e. So what is the derivative at s over e? It's 0. If x is greater than s over e, what can you tell me about its derivative? It's negative. If x is less than s over e, what's the true of the derivative? Positive. So they're doing it, but it's got to look something like this. So the integer max has to be immediately to the left or immediately to the right of S over E. So by converting this from a discrete problem to a continuous problem, we solved the continuous, and then we were very fortunate by just doing some simple curve sketching to know that the discrete max has to be the right before or right after. All right, so this is a good place to stop. It's still 11:50, so we got it in.